We're going to take what we've done over the last few days now and apply it to a situation called relative motion. We also call those navigation problems because the relative motion problems end up being typically problems where maybe the captain of a ship is navigating or the pilot of a plane is navigating, although it doesn't have to be. That's usually what it ends up being. If we take the most simplest form of relative motion, then the question might look like this. An airplane is traveling 800 kilometers per hour to the east, and a baseball is thrown inside the airplane at 100 kilometers per hour. By the way, I wouldn't suggest you do this. Okay, this is enough to probably get you arrested if you throw a baseball at 100 kilometers per hour inside an airplane in the sky. But if you did, what would be the velocity of the baseball, the relative velocity of the baseball? In other words, the velocity relative to the ground. Okay, relative to the airplane, it's moving at 100, right? Like, end of discussion. Relative to the airplane, it's moving at 100. But relative to the ground, if there happens to be somebody standing on the ground watching this glass airplane fly by and can see inside what's happening, the baseball is moving at what speed or what velocity relative to that person? Either 900 or 700. Good. Depends on which way you throw the baseball, right? Okay, you ever walk on one of those moving walkways at the airport? Yeah, you know what I'm talking about? Okay, it's moving at, let's say, 4 meters per second. Okay, if I walk at 4 meters per second with it, okay, relative to it forward, then I end up moving at, relative to everybody else that's standing beside it, 8 meters per second, right? But if I walk backwards on it, and that's what I like to do when I go to the airport because it's a lot more fun to walk the wrong way on it. Okay, if I walk backwards on it at 4 meters per second, then what happens to me? Relative to you who's standing over there on the side, I'm not moving at all, right? To find the relative velocity, that all we got to do is add the vectors together. The moving walkway was 4 to the east. I'm walking 4 to the east relative to the walkway. My velocity relative to the ground is 8 to the east. If I'm moving at 4 to the, the walkway is moving at 4 to the east, and I'm moving at 4 to the west relative to the walkway, then I add those up. 4 plus negative 4 is 0. My velocity relative to the ground is 0. You want to find the velocity, the relative velocity. All you got to do is add the vectors together. 800 plus 100 is 900. 800 plus negative 100 is 700. Make sense? We added these vectors together, right? We added them together. But we did pay attention to positives and negatives. When we're finding the relative velocity in one dimension, we add vectors together. But pay attention to positive and negative. Well, listen, when we're finding a relative velocity in 2 dimensions, we're still going to add the vectors together. But 800 plus 100 is no longer 900 or 700. Now, 800 plus 100 is something else altogether. We know that when we add vectors in 2 dimensions, we have to draw a vector diagram, a right-angled triangle vector diagram, and then do your thing with the Pythagorean theorem and a little bit of trigonometry. All right, what does this look like? Okay, what does it look like in practice? Maybe a question looks something like this. Maybe we say the pilot of an airplane flies or heads, right, aims west. Okay, that pilot wants to fly to Vancouver, so he or she heads west. But yet there's a wind to the south. And that wind takes that airplane off course, right? You know, if you're aiming to the west, but there's a wind to the south, then the plane is going to go off course. How many of you guys drive? Okay, you guys know if you drive, when it gets really windy out there during a Chinook, the wind is blowing from the west to the east. Sometimes you're driving north to Calgary. You ever notice this? And your steering wheel is like cranked like this so you can stay straight on the road. Right? You're aiming over there somewhere towards like Canmore or something in order that the wind that's pushing you over this way ends up taking you in a straight line. Here's what we do. When we add these vectors together, we say that the vectors that contribute to my actual motion, the vectors that contribute to my motion are what we call solid line vectors, or the normal vectors that we're adding together. Okay, the vectors that are contributing to my motion are the vectors that I'm adding together. The vector that is my actual motion, in other words, right, when I aim towards Canmore and the wind is blowing towards Regina and I end up going, my actual motion is north towards Calgary, my actual motion would be my hypotenuse. Or not my hypotenuse, not necessarily my hypotenuse, my resultant vector. Make sense? So resultant vector is where you actually go. That's your relative motion, your resultant motion, your resultant vector. The vectors that contribute to where you go would be the ones that I add together that have to be drawn front to back or head to tail. So in the case of, what was the first example I gave you? The airplane heading towards Vancouver. Well, that's not where I'm going, right? But that's contributing to where I'm going. So I'm going to draw that vector as a vector that I'm adding to another vector. But there's a wind to the south. That wind also contributes to where I go. Add together the vector that is where I'm aiming and the vector that is the wind, and what do I get? My resultant vector, which also happens to, in this case, be the hypotenuse, happens to be, this is the vector that is my actual motion. When I aim to the west and there's a wind to the south, where do I end up going? Somewhere southwest. Right? Just like in this one, where I added 800 plus 100, or 800 plus negative 100, to give me 900 or 700, this time I'm adding vectors together as well. But I'm adding them together in 2 dimensions. Good news, I already have a right angled triangle. No funny angle to deal with, right? And that's going to be the way that it usually is in these questions. And that's why mathematically, as I said before, these ones end up being easier. Around. First question says, the pilot of an airplane heads directly north at a velocity of 200 kilometers per hour. Probably nobody in here flies airplanes, right? Do you really? Yes? Okay, good. It's not, do you really? Yeah, it's not very often that I actually get somebody that flies, but occasionally it happens, right? It's funny that you can actually learn to fly an airplane before you can drive a car, right?
You can learn, but you can't be licensed.
You can't be licensed, okay. Okay. So, William, you're flying this airplane, you're heading directly north to Edmonton at a velocity of 200 kilometers per hour. That doesn't mean you're necessarily going to go directly north, right? There's other factors that contribute to where I actually go. Where I aim is certainly one of those factors that contribute to where I go, right? So that's a vector that I want to add to another vector. I'm aiming directly north, or William is aiming directly north at 200 kilometers per hour. Added to that is a vector that also contributes to where I actually go, or where William actually goes. That's the wind. So we're heading to the north, we're aiming to the north, which contributes to where I go. But there's a wind to the east, which also contributes to where I go. We're going to add those two vectors together to get where I actually go. Now, we can solve for the value of r. How? Sorry? Yeah, it's the Pythagorean theorem, right? Square root of 200 squared plus 50 squared. We'll do that in just a second here. We're going to solve for the value of theta as well, because it might be useful if you're flying an airplane to know where you're actually going to end up. Reality is you're probably going to, if you want to go to Edmonton, you're probably going to set it up so that you go to Edmonton, not aim to Edmonton, and then end up somewhere in Saskatoon or whatever. But what angle am I going to end up at here? Which one am I going to solve for? 1, 2, or 3? Which one? Yeah, it's angle 3 here, right here. Good. We'll solve for r using 200 squared plus 50 squared. And we'll solve for theta using the inverse tan of 50 over 200, right? Opposite over adjacent. What does that r value work out to be? 206, or we're going to make it 2.1 times 10 to the 2 kilometers per hour. So look, I'm aiming at 200 kilometers per hour, but I end up going a little bit faster, right? Because of the wind. Now, the wind's not a tailwind. If the wind was a tailwind, I'd end up going at 250 kilometers per hour. Or if it's a headwind, I'd end up going at 150 kilometers per hour, right? It's off to the side, which makes me go a little bit faster, but also takes me off in another direction. What is that value of theta? Anybody solve for that? 14 degrees, and that would be 14 degrees east of north, because you can see here, I'm going north and I'm going east, but I'm measuring my angle from the north, so it would be east of north. So I aim to the north, but there's a wind that takes me to the east. So where do I end up going? At 14 degrees east of north at a velocity of 2.1 times 10 to the 2 kilometers per hour. I have one more to do with you as well, and then we're going to wrap it up for the day. This one is a little bit different. This is a ship going in water. Captain of a ship aims her ship at 20 kilometers east, at 20 kilometers per hour, but there's a current of 10 kilometers per hour that puts the ship off course. Where does the ship actually go? Well, these first two vectors are contributing to where I go, right? So those are my vectors that I'm going to add together. We aim 20 kilometers per hour to the east. It doesn't say which way the current is. Does it say it on your sheet? No? Okay, let's say the current is to the south. We're adding the two vectors together that contribute to where I go. The resultant vector is where I go. So we're aiming to the east, but yet there's a current to the south. Where does the ship actually end up going? It goes down here, the resultant vector. Okay, we solve for the value of r, and we solve for the value of theta. R is equal to the square root of 20 squared plus 10 squared. What's that number? 400, 500, square root of 500 is 22, I want to say. Until somebody tells me different, that's what it is. And then theta is the inverse tan function of opposite over adjacent, 10 over 20. And the angle is 27 degrees, rounded to 2 digits, and we're going to say that's 27 degrees south of east. 27 degrees south of east. Okay, it's south of east because, look, we're going to the east and we're going to the south, but the angle is measured from the east. So south from the east, or south of east. Right, Josh? Got that copy down? You should do that.
Good afternoon, everyone.